Hello everyone, and welcome to this introductory tutorial on how to use the SchrodingerWave program. So I designed this program during the past semester, and in this video we are going to talk about the environment of the program and a little bit introduction on how to use the program, as well as how to simulate a very simple system called particle in a box. We will discuss a little bit on what the particle in a box system is, and we will discuss the physics of the particle in a box, and then we try to simulate the system and compare the analytical result with our computed results using the program. Next, we will learn how to visualize the program, the results, using the program, and we will have a little discussion about the resolution and accuracy of the program at the end of the video. Before starting off, I want to mention that the program can be downloaded from this web page. And if you go to this web page, there are guidances on how to install the program, and you can follow the links, and there are several options on what method you want to install the program on your computer. After you go ahead and install the program, you will see a screen like this, a window like this. Let me go ahead and actually start the program so that you can guys see. So this is the program that I've already installed, and I've started the program in the Windows. And you can see that there are three menus on the upper left corner. On the right section, you see lots of different options that are related on how to design the potential energy. And there is also one option here on how to visualize the system, visualize the result. So without further ado, let me start by changing how the program looks. So after coming through themes, you can change how the program looks. For example, I've chosen white because it's much more elegant if you use the program in this section. If you are a Rice University student, you might be interested in adding more owls to this program, and you can add more stickers by just clicking on the Rice University logo, and you see my name and the professor who helped me develop this program. And you see another owl that's really added. You can add even more owls if you come to the themes and show more owls. So if you let me go ahead and try to design a potential. First, let's design a finite square well potential. It is a square well that has a finite depth to it, and the finite depth can be changed by this value, by changing this value. If I hit the run button, you see that somewhere in the so we have the X position, and at this X position, the 40% value of this 50 is around here, actually 20, and the 60% value is 30. So between 20 and 30, you see that the left wall and right wall of the our well is positioned, and the well depth is actually 2. So we can actually go ahead and increase the well depth. I'm going to put the value of 4. And if I hit the run button again, you see that the well depth increases. You can change the wall position as well. Let's go, instead of 40% and 60%, I'm going to choose 30% and 70%. So you see the well depth widened. This program is designed so that user can actually go ahead and add multiple different potential profile on top of each other. For example, I can select finite square well and finite square barrier at the same time. And if I come here to the barrier option, you see that the barrier will be from 45% to 55% of opposition, and it will going to have the barrier height of 1, or let's choose 1.5. And if I hit the run button again, you see that there is a well and there is a barrier right in the middle of our well. So you can go ahead and design different potentials. You can, I don't know, add a harmonic oscillator. Let me just increase the force constant here. And if I just add a harmonic oscillator, see that there is a quadratic potential right in the middle of the barrier. So we have a well, a barrier, and a harmonic potential right in the middle of our system. So the power of this program is just not, you're not limited to these finite set of potentials. You can select many different 1D potential. You can actually design any 1D potential using any other external program like Excel or like MATLAB, for example, and you can import that potential right into the program. And the way to do this, I'm just going to unselect all of these options and select the imported potential. And I'm going to the import tab and import the potential that I've previously designed. So this is a test potential sine. It's a sine function that I've previously designed, and you can see as I import it, it shows the potential here. And as I hit the run button, you see that the potential is imported here. The green plot is actually the wave function that is computed by our system. And you see that it has negative values. You can go ahead and change the eigenstate. For example, right now we are in the ground state. We can change the eigenstate here, and you see that what's happening is as the potential energy changes, so does the plot is also shifted shifted as we go ahead in the quantum numbers. To show what I mean, let me just choose the harmonic oscillator, and I'm going to widen a little bit curve here, and let's start from 1. You see that the green curve is right near 1. It's around 1 hertz, 0.63 to be precise. And as I increase the quantum state, the eigenvalue is printed here from 0.63 to 1.9. And the green curve is also shifted up. Let me do it again. It shifts from 2 to some other value, 3. And that's a really helpful feature, especially if you're using the program in the multi-visualization mode. So if I turn on this switch, you see that the multi-visualization state is on, so that you cannot use the single visualization state anymore. So if you use the multi-visualization state, you can actually go ahead and visualize multiple states all at the same time. And that's a really nice feature, that it actually shifts each potential, each wave function by its eigenvalue. What you can also do is turn off this feature. You can actually turn off this feature if you don't need it. If you do not need to visualize multiple states all at the same time, you can come here in the setting, and you can come to the shift wave function by energy and disable this feature. So if I run 3 versus 5, all of them are on 0. If you're a quantum chemistry student or have studied quantum physics or quantum chemistry back in college, you might be familiar with the notion you're certainly familiar with the notion that the wave function itself most of the time does not have meaning. And what has physical meaning most of the time is the square of the wave function rather than the wave function itself. And if I turn on this feature and hit the run button again, you see that the square of the wave function will be plotted as well as the wave function itself. We can also go ahead and also I don't know if I talked about it or not, but you can actually come here and export the potential that you've made using different combination of different values. You can actually come here and export that potential here, export potential, and I'm gonna call it export 2. And if you forget on what the problem was, you can actually come here and import the previously exported potential here. And that's a really nice feature as well. So let's go ahead and discuss about what I've promised you before and earlier in this video, and that's the particle in a box system. So what is a particle in a box? Particle in a box is a really, really simple model. It is, in fact, the simplest model for which the quantum Schrodinger equation can be solved. So it simply is a one-dimensional, the one-dimensional particle in a box is simply a one-dimensional potential that from 0 to the L, length of the box, L stands for the length, and from 0 to L, you have 0 potential energy. But as you step outside of the box, the potential energy goes to infinity, which means that you are not allowed to be in those regions. So you're truly trapped inside the box. You can go ahead and solve the Schrodinger equation for this system. But before that, you might ask, why do we need to solve this system? What's nice about this system that we want to solve it? Well, first, it's a simple and elegant system. Most college students have heard or worked with it at least once. And we have an analytical solution to the Schrodinger equation for it, which is very important because we have an analytical exact solution that we can compare our computed answer to which is a nice feature. So we are going to solve this particle in a box system using our computer program, as well as the analytical solution, and then compare the two solutions together. So if you write down the Schrodinger equation here, and I'm not going to go into the details on the Schrodinger equation, you will understand that we have a wave function, which is a sine function for this system, and energy, which depends on something called n, which is a quantum number, and also the mass and length of the particle, length of the box, I'm sorry. So you have energy and you have wave function, which are depicted using this formula. And as I mentioned, they depend on the quantum number n. And the energy depends on the square of n squared. So if you plot the values of energies here, you see that I've drawn the spectrum for the first 4 states. You see, and let me mention that it is not scaled here. However, you see that they are discrete. In other words, the energy is only allowed to have these discrete values and not the energies in between them. And if you plot this sine function, you see that for the first eigenstate, we have a half a sine, and we have a complete sine function, and we have 1.5 and 2 sine function. and further, and so on and so on. So in order to visualize these results using our application, let me go back to the application itself. Just bear with me. So if you come here and the application itself, you see if we do not choose any potential setting, so the potential energy will be 0. And let me go ahead and hit the run button and change the quantum state from 5 to actually 1. You see that the wave function is kind of a sine, half a sine function as we saw in the slides. But here, the half a sine function is somehow negative. We saw in the slide that it was a positive sine function. It was upward. Here it's negative. It might be strange. However, the wave function is squared as we expect. It is positive. What else do we see? We see that the potential energy, which is this blue curve here, is 0. You don't have any blue curve here because it is 0. And if I zoom out, you see that outside of 0 to 50, our position is, our space is spanned between 0 and 50. And this is the same in every setting using this program. The space is always spanned between 0 and 50. And if you zoom in, you see that nothing is outside of this box. So this system is truly a particle in a box. It's a particle trapped in a box of length L equals 50. You might ask, what is the unit of the L, or maybe what's the unit of the energy? We will discuss about that later in this video, but to give you the answer, they are in Hartree. They are in Hartree atomic units. So what we have is actually a particle in a box with a length of 50. The box with a length of 50. So if I go ahead and increase the quantum state here, you see that I can observe all those states that I talked to you about. So we have two sine function in the n equal 4. And the energy is also printed here, 0.03 Hartrees. What else do we see? So let me go back and discuss about why we see a negative curve instead of a positive one. So let me go back to my slides. So after we solved the Schrodinger equation, we saw that our wave function, or psi, has a form of a sine form, sinusoidal form, and our energy is also discrete and depends on an n, which is an integer number. It depends on n squared, to be more precise. And the Schrodinger equation gives us back the wave function itself, and that's how the Schrodinger equation is supposed to behave. You might notice that actually if we multiply both sides of the equation by -1, the equation still holds. In fact, if I multiply it by a number like I, which is a complex number, it's imaginary number, the equation is still true. And no matter whether you have a positive function or a negative function, the equation is true. So it turns out that both of these solutions, whether the positive one or the negative one, or even the imaginary one, both of them belong to the same state. There is, if you actually solve the time dependent Schrodinger equation, you will understand that both of them belong to the same state and they are just in different phases. So the only difference between these two figures is their phases. They're out of phase with each other, but they belong to the same state. However, in the physics, as I mentioned before, what actually matters is not the phase of the wave function, but it's squared. So if you actually square it, and that is the density of the probability density of finding a particle, it will always come out positive. And it does not actually depend whether it is imaginary or whether it is positive or negative. It will have the same shape for its square value. And so let's go ahead and talk about our last part of the talk, which is the resolution. But before that, let me explore the ways by which you can actually visualize the result. I've already mentioned about the wave function squared feature, as well as the multi-visualization state and single visualization state. But let me just go ahead and increase the wave quantum number. And as I increase the quantum number, you can look at this eigenvalue, which is printed here. And you see that the eigenvalue energy is increasing, as we might expect, by increasing the quantum number. In fact, we saw in the slides that it has a square relationship. As we go from 2 to 4, we might expect that the energy grows by a factor of 4 rather than by a factor of 2. So to visualize the energy, we can actually come here in the setting menu. We can show energy spectrum. And we can come here and select and plot eigenvalues. So it asks you what's the range of the eigenstates you're interested in. Let's plot the first 10 or first 15 eigenstates. And after a while, the program spits out this graph. And as you expect, it has a quadratic function form because it depends on n squared. As we might expect, this is a quadratic function. And you can see that for the first quantum state, the energy is 0.002, and it grows quadratically with the increase of the state, quantum state. Let me go ahead and instead of first 15 states, plot all the possible states that I can visualize. So here, I'm allowed to plot from 1 to 1,000. And I'm going to discuss why 1,000 in a few minutes, but let me just put 1,000 here. And you can see that just move the window to the screen. Oh, something happens. It is not the quadratic function I expected. And that's a little bit strange. So I expected the quadratic function. Maybe it is the labels that are deceiving. Let me just disable the labels here. So I can come here in the setting. When I come to the show energy spectrum option, can actually change the energy spectrum plotting option by changing the plot type. So far we have been visualizing the energy spectrum using bar with labels. I can actually select bar without labels, or I can select line and symbols. So let me select that and visualize the energy spectrum from 1 to 1000, and it is actually not the quadratic function that I expected. It looks quadratic from 0 to somewhere around 400, but it starts to deviate from the quadratic behavior in the middle of the graph. So let me see if I can change this. There is an option that you can change the resolution, and the resolution is actually the number of basis sets that this program uses to compute the wave function. So in the high menu, the number of basis sets is 5,000. In the middle, which is the default, in the medium resolution, the number of basis sets is 1,000. That's why you see that 1,000 is the maximum number that you could choose previously. And in the low resolution, the number of basis sets is 200. So the reason why you might want to switch the resolution is the speed of the calculation. If you're using an old computer, or you're not having access to a fancy computer with 7 cores, or 8 cores on it, you might want to switch to low resolution mode. However, if you want to just go ahead and have higher accuracy, want to have a better accuracy, you might want to change the highest resolution mode. So I'm going to do that. I'm going to change the 5,000 basis sets here. The resolution is set to high, and let me go ahead and hit the run button again so that the change in the setting is taken into the effect. So if I hit the run button here, you see that the program is a lot slower because the number of basis sets has increased. I can come here and again plot the number of different states. And as you see, the maximum number of states that can be chosen is 5,000 rather than 1,000 in the previous example. Just okay, so you can see that it is still behaving the same way. It is the energy, however, in this case, is still quadratic up to 2,000, but deviates from the quadratic behavior again in the middle of the graph. However, it has a really good behavior up to thousands, which is really good because in our previous example, it was around 400. So what I can do actually is actually come here and export all the values, all the energy values that are computed here. I can come here and find, export eigenvalues. And as I export eigenvalues, I can say eigenvalues here. And if I come here, you see that all the eigenvalues is printed in a comma-separated file, comma-separated value file, which can be opened using any spreadsheet program. And this is the first quantum state, the energy of the first quantum state. The units are in heart rate, and you can go ahead and see that it goes down to 5,000. So you can actually use these values and compare them to the value of the analytical solution. And that's actually what I've done. I'm going to share that with you. So let me go back to the program. So here is a discussion of the Hartree unit. You can find this discussion in the LibreText website. You see that one Hartree is about 27 electron volts, and which is 2 times the energy of the hydrogen in the ground state. So let's go back to our discussion about the energy. And as I mentioned, the energy versus quantum state should have a parabolic behavior, a quadratic behavior. And this can be observed in this graph. And if we analyze the eigenvalues, we see that for the lower quantum states, whether we are using the low resolution mode or higher resolution mode, low resolution mode being 200 basis set, higher resolution mode being the highest one is 5,000 basis sets. Whether you're using the lowest or the highest, you see that there is a very good agreement between the analytical solution and the computed results for the first 60 or 50 quantum states. It starts to deviate for the low resolution mode in 60. And if you look at the relative error here, that in like after 50, after quantum state 50 or maybe 60, the error gets above the 5%, which is a very estimated number for the acceptable error that we can accept. And you see that the error for the 1,000 or 5,000 is pretty acceptable, pretty negligible compared to the analytical solution for the highest resolution mode. However, if you go to higher quantum number, you see that the relative error grows very quickly. In fact, that 5% threshold that I talked to you about is met for the lowest resolution mode around 50 or 40 quantum state. For the medium resolution mode, it is around 300 or 200. But for the highest resolution mode, it won't happen until like 1200 quantum state, the quantum state number 1200. So you see that the resolution is actually playing a big role in the accuracy that we might get from our system. The higher the resolution, the slower the program is. However, the cost that it pays if you go to the lower resolution mode is actually the accuracy. Here is the same plot for higher quantum numbers, and you see that the analytical solution is the black one here, and the blue one deviates from the black one pretty quickly, but the green one remains loyal to the analytical solution until 1400, but it starts to deviate from that after that. And the relative error for the quantum states is shown here, and it can go up to 60% error. So it means that for higher energy states, the output of the program should be treated with caution. It should not be taken very seriously. However, for the lower quantum states, the program is able to print out very good value and very good results, which with relative errors below 1%, which is really fascinating. However, you should be cautious about higher quantum states. But that's actually what most of physicists actually need, because what we need is to actually, I've never gone above 50 or 60 quantum number, because we are interested mostly in the ground state and the states near it. So you might never want to go above a certain limit. So you might ask why this program has a limited resolution at higher quantum states. What is the underlying reason? What's the physical meaning of that? That as we increase the energy, as we go to higher quantum states, the program starts to misbehaves, the error grows, and the results are not quite acceptable. So the reason is explained in the next slides of the video. Let me, you may recall that this is the behavior of our quantum system in the ground state, quantum state number 1. And let's imagine that we are studying this system using an instrument, whether it's a theoretical instrument like this program, or whether it's an experimental instrument, I don't know, using a spectroscope or microscope or anything else. So we are studying this the behavior of system using an instrument, but that instrument has a limited resolution. A limited resolution, by which I mean that it cannot see the behavior, the smooth behavior of this graph. Rather, it sees pixel by pixel. It sees this graph pixel by pixel, and it has a limited sampling frequency. For example, it cannot distinguish between these points. Let me just turn on my laser pointer. I'm sorry. It cannot distinguish between this point and this point, or maybe this point and this point. So it's sampling just the middle point, and it just represents that as that region, that range. So let's say our instrument has a it just measures the middle point of these pixels, and is not able to actually increase the resolution. The resolution is limited. So if we measure these points, the output signal that our instrument is measuring looks like something this. You see that it has captured pretty well the behavior of our system. However, it is not as smooth as it is in the upper graph, and the reason is obviously because of the limited resolution. It might not be a big deal for this quantum state number 1, but as we go to higher and higher quantum states, you might see that this will change. So, and this animation, you see that as I go to higher and higher quantum states, what our instrument is measuring is completely different than the real physical system. So the real physical system behaves like a sine function, as it should be, because it's a particle in box. However, what we are measuring, the x position is stayed the same. However, the y position is always changing, and it's completely different for each state. We might have one state which is all our points are measured 0, and our instrument might say there is no particle in this box. However, that's not the case. We might have a situation like this, that for quantum state number 44 and quantum state number 35, we might measure the same behavior as quantum number 1. And because what we have measured has not this correct sampling frequency. That's what Nyquist theorem is about. So, and this is the reason why the system deviates in the higher energy states. And this happens as a result of the wave particle duality of matter. And that's described by de Broglie wavelength. So de Broglie wavelength is just described by this equation, and it states that the higher the kinetic energy, the higher the momentum of the particle is, the lower its wavelength. Here we have a smaller wavelength than here. Here we have a larger wavelength, and the larger the wavelength is, the lower the kinetic energy. And as we increase the kinetic energy, as we go above those quantum numbers, the wavelength decreases and decreases, And as it decreases, at some point, at some threshold, it surpasses the resolution of our instrument. And that's where it starts to deviate. So with that, I'm going to just give you another example for this behavior and sign off. Okay, so let's go ahead and choose the Morse oscillator. So this is the behavior of the Morse oscillator. Let me go ahead and change the resolution to medium so that the speed is a little bit more acceptable. I'm going to also change some potential settings here. Okay, so here we have an uphill behavior. So the system, as you might expect in the lower energy cases, is in the downhill. But if we increase the energy, the system might actually have the enough energy to come here, like a marble that is pushed and have the energy to go uphill. And it can be found in the upper heights as well as it gained enough kinetic energy. So let me go to quantum state number 700. You can see, let me just also increase. I'm going to enable the file. What I did, I just enabled that it can shift the wave function. And you can see that the particle is actually gained enough energy so that it has actually surpassed the mountain. So I've gone too far. Maybe I can come a little bit down below. Maybe 100. And as you see, as I increase the as I increase the energy, the wavelet decreases, and it decreases more and more. And as it can be seen here, this wavelength here is so small that it might have surpassed the resolution of our system. So I'm not gonna very much trust the behavior of the system here because the wavelength might not be very well displayed here. If I go above a certain energy, you see that it's not wavy anymore. It's like a single line. And that happens because it's called Morse correspondence principle. And we see that it behaves like a particle. It's not wavy anymore. Or the resolution of our instrument is not enough to observe the quantum behavior anymore. And with that, I'm gonna thank you all for staying up to the last part of the video. I hope you enjoy simulating with this program. And I hope that if you have any suggestions or questions, please reach out to me using the email address provided in the webpage. And thanks for watching. If you like this video, please hit like or subscribe and share this program with your friends and colleagues. Thanks again, and have a good day and night.